Hey guys, in Unit 2 we're going to talk about atoms and the periodic table. In Notes A, we're going to focus on atomic theory and atomic structure. You may have heard the term that atoms are the building blocks of matter. They are the smallest particles that any element can be broken down into. Beyond that, the protons, neutrons, and electrons lose properties. So the atom would be the smallest particle that an element can break down into while retaining those properties. This concept actually came from early Greece. A scientist named Democritus had this idea that atoms had, he didn't necessarily call them atoms at first, but he had this idea that at some point there was this small particle that had unique properties. Now we know a whole lot about atoms. We know protons and neutrons are focused in the nucleus and that they contain most of the atom's mass. We also know that electrons circle around the nucleus in what we call the electron cloud. In a few notes, Note C, we're going to get into the electron structure a whole lot more closely. But for now, you should know that electrons are on the outside of the nucleus. So here we have Democritus. So the first concept of an atom was a long, long time ago, 400 BC. And he did have this idea that if I look at this rock, I can break that down and break that down, and I can get half a rock and half a rock and half a rock until at some point you can't break that down anymore. There is a small unit that cannot be divided that is just a rock piece. And that is different than if I look at a bucket of water and I can break that down to smaller and smaller pieces of water, but at some point there's a water particle, or maybe he didn't know the term particle, but like a piece of water, and that smallest piece of water is different than that smallest piece of rock. This was more of a philosophic idea than a science idea. Science didn't necessarily exist in the way that we know it at that time. So he was just kind of thinking, well, these are two different things, but that was a very innovative thought at the time. So the word atom actually comes from this very first idea before the beginnings of modern science. So back in 400-ish BC, his records were kind of shoddy back then, right? That's when we had this idea of, oh, this is this small indivisible piece. And so that's where the word atom comes from, the Greek word atomos, which actually means unable to be divided. Now we know of subatomic particles, but the fact remains that an atom cannot get any smaller without losing its properties. So an atom is still something very special. A long, long time passed from the early 400 BCs up into the 1800s before we had any more scientific-ish developments. Again, not necessarily modern science yet, but before we really put any thought into developing science, there was a lot of things happening in the meantime. But finally we make it to the 1800s, and John Dalton comes out with his atomic theory. Some of these things are still true. Some of these things are not so true anymore. But as of the early 1800s, this was his theory. Remember, theories explain. So his theory is going to just explain what the smallest particles might do. So postulate 1, all elements are made of tiny atoms. So this sets the premise that atoms are the building blocks of matter. Postulate 2, atoms cannot be subdivided. Now we know that they can be divided into, we have subatomic particles, protons, neutrons, and electrons, but they cannot be subdivided without losing their properties, which is important. His third postulate was that atoms of the same element are exactly alike. He's mostly true, but take out that word exactly, because we have ions and isotopes. His fourth postulate, atoms of different elements can join to form molecules, which is pretty much true. Hydrogen and oxygen can combine to form water. However, it is also true that atoms of the same element can join to form molecules as well. Like O2 would be 2 atoms of oxygen, which would combine to form a molecule. So with a few adjustments to his atomic theory, we can still represent what we know to be true now. Thomson and Milken were the first scientists to actually start thinking about the structure of an atom. Up to this point, we had only thought about what an atom kind of is, more in a theoretical sense, but they started actually thinking about what's inside of an atom. So they discovered the first subatomic particle, the electron. They did this using something called an oil drop experiment, and the most famous piece of this experiment is the cathode ray tube pictured here. They were able to use positive and negative plates in order to determine that there was a negative part inside of an atom, which would be repelled from the negative side of the plate, attracted to the positive side of the plate. So the motion of the atoms as it went through these plates was able to give them an indication that there was a large negative part of the atom. They developed a theory called the plum pudding model. In the plum pudding model, we had an atom that had just floating electrons. They did not know about the nucleus, and they did not think that the electrons actually had any motion to them. They just thought they were spread out throughout the atom, kind of like chocolate chips would be spread out through a chocolate chip cookie. I guess plum pudding, plums being spread out in pudding, was more of the era. You get the idea that the electrons are floating around the atom. That is their model, known as the plum pudding model. Our next scientist in the development of the atomic theory is absolutely the most famous. This is Rutherford. He discovered the positively charged nucleus in one of the most famous experiments there is, the gold foil experiment. What he did is he set up a piece of gold foil, shown in the center here, and he passed something called alpha particles, which we'll get into later, but basically know that they are very, very positive. Those positive particles passing through atoms, which at this point we thought were uniformly negative, should have passed through no problem. But instead something unexpected happened. The alpha particles got to the gold foil and they were deflected. They moved in ways that were never expected, even back towards the particle emitter. The only explanation for that was that something inside of the gold foil was also positive. And so as he developed this theory and did more and more experiments like this, he was able to determine that inside of the inside of the atom, we had this positive center, which he then named the nucleus. At this point, though, they still think that the electrons are just floating around. So picture plum pudding model with a nucleus in the middle. As it turns out, those electrons aren't just floating around on the outside like chocolate chips and cookies. They're actually moving, and they're moving in a very organized way. They're moving in orbits, much like the planets orbit the sun. So this is Niels Bohr, our next scientist in the development of the atomic theory. He discovered that there are different energy levels in which the electrons orbit. The electrons are confined to move only in the set energy levels. Kind of like on a bookshelf, you can't put a book in the middle. You have to put it on one shelf or the other. The electrons behave the same way. They can only go on one level or the other and never in between. Only specific orbits are allowed. Due to the similarity of how closely this looked like the planets orbiting the sun, his model was actually called the solar system model. Bohr's model almost brings us completely up to the modern atomic model, with one small tweak we still need to do. Bohr assumed that the electrons were moving in a straight circle, because that's what the Earth does, moves in a straight circle. Yes, the Earth both revolves and rotates, but that revolution around the sun is going in a straight path. The electrons are a little bit more complicated. They go in a wavy, wiggly path as they rotate and the electrons are revolving. So there's a very complex motion. That's something that Schrödinger helped us develop. So his contribution is known as the wave functions. He developed wave mechanics, or you may have heard this called quantum mechanics. which is describing the electron's motion in a very complex wave function as it goes around the nucleus. With all that being said, one of the most important things you should know about electron motions is that electrons are lazy. Electrons like to occupy the lowest possible energy level. So the electrons will fill low energy levels and build out, which is a huge principle we're going to get into as we go through this unit. And as they move out, as the energy increases, the distance increases. Before we move into more about electrons and quantum mechanics, just kind of wanted to give you a sneak peek of how complicated wave functions and wave motions can be. This is Schrödinger's equation. This equation is used to determine the probability of finding an electron in an atom. Don't worry, you don't need advanced calculus for honors chemistry, I promise. Alright guys, it's time to get our feet wet in a little bit of quantum mechanics. This is one of the more difficult areas of Unit 2, so if you need a stretch break, pause the video now, stretch, come back with your full attention, because this is going to be super important and it's a little confusing. What we're about to look at are the orbitals. So an orbital is an area, or it says region, a region in the atom where I could find electrons. The thing about electrons is we cannot define exactly where they are, because by the time we calculate where they are, they will have moved. So all we can do is find the probability of where they should be. To add to that, the act of observing where an electron is will change where they are. There's a concept called Schrödinger's cat where it kind of insinuates that your actions can influence the outcome. So the idea here is that we are going to try to make sure that we capture the electron is in here somewhere. So this is all about probability. So we're defining regions. These regions will show you where the electrons should be in an atom. So there are 4 different types of regions, or 4 different shapes of orbitals. The first shape is called the s orbital, and it's a spherical shape, shown on the left of the screen. A spherical shape is the same no matter which way you turn it. So we would say that there are only one s, or there is only one s orbital. The p orbitals are dumbbell shaped, and they can orient along each of 3 axes: the x-axis, the y-axis, and a 3-dimensional axis known as the z-axis. So we could actually have 3 different orientations for p orbitals. Our next 2 orbitals get very complicated in shape, but I want you to notice a pattern. The first shape was an s orbital, and there was only 1 of those. The second shape was a p shape, and there were 3 of those. Our next shape is d. There are 5 of those. And then the last shape is f. So 1, 3, 5, what would come next? 7. So if you can get that down before we learn electron configurations, you'll be well off. There's 1s, 3p, 5d, and 7s. 7f. And they fill in that order because electrons are lazy. S would fill before p would fill before d would fill before f. S, P, D, F, 1, 3, 5, 7. Something to memorize. Here are a couple little acronyms that might help with the order. Santa Paulette Donut Factory, or Some People Dance Funny. SPDF. And also remember, 1, 3, 5, 7. So that's all we've got for today for a quick little intro into quantum mechanics. A lot more to come on that with Note C. Make sure you've got the memorization down on that SPDF. Let's move on to valence electrons. So valence electrons are the outermost electrons, the ones that are furthest from the nucleus. And the absolute most important thing that you should know about valence electrons is that they determine how an atom will act in a chemical reaction. They drive 100% of the chemical properties of an atom, which is why atoms in the same column have similar chemical properties. So the number of valence electrons will determine the chemical properties of an atom. You can actually tell how many valence electrons an atom has based on where it is on the periodic table. Valence electrons were very important in determining the organization of the periodic table. So we should probably talk about the father of the periodic table. This is Dmitri Mendeleev, the father of the periodic table. There are so many hidden patterns in the periodic table that we will also talk about this unit, by the way. It was quite an impressive feat for him to put this together. But I should mention he made one mistake. As he went from left to right, he arranged the elements in order of atomic mass. That's not the way it is today. It was Moseley who realized there are a couple things that are out of sorts. There are a couple things that aren't in the same column with like properties. So he decided it made a lot more sense, and it does, to organize by atomic number. What was the atomic number again? We defined that in Unit 1. The atomic number is the number of protons. So when he organized the periodic table by atomic number, everything fell into place. Something I just want to acknowledge real quick. He was in the middle of his research when he was drafted into World War I and actually died at war. So, awesome soldier and awesome contribution to the scientific community. Speaking of the periodic table, let's get into a little bit of vocabulary that's going to help us as we discuss it. First, there's this weird word called periodicity. Basically, this means periods, patterns. Periods are repeating things, so patterns of the periodic table. So when we looked from left to right or up and down, column versus column, we're going to study lots of different patterns. So periodicity is all about the patterns. There are also different names for the columns versus the row on the periodic table. A horizontal row, horizontal like horizon, would be called a period, and there are 7 different periods on the periodic table. I also want to point out, you can see with the color coding here, that as we go across the second to last row, or the 6th row of the periodic table, that would include one of our little cutouts at the bottom here, what we call the lanthanide series. And then as we go across the very last row, which actually is all the way filled out now, would also include the very last column, or the anthanide series. So these little cutouts go actually into the spaces here. It's kind of like cutting out Alaska on a map. It belongs there, but you know how big the map would be if we actually included all the space in between. So same thing with the periodic table. They kind of did a cutout so it would fit on like a normal piece of paper. Generally speaking, as you go up and down the columns, we have groups, sometimes called families, because they have similar properties. We kind of leave off this middle area. Those are transition metals as a whole, and they are kind of a group in and of themselves. But all of the other columns on the periodic table would be separate families. Now let's look at a block on the periodic table. Here we have the block for carbon. The atomic number is always on the top. So the number on the top of the periodic table is always the atomic number, and the atomic number is always called the number of protons, or it always equals the number of protons. Then you would have the atomic symbol, the element symbol in the center, and then depending on your periodic table, most of them also include the element's name. And then at the bottom, you're going to have a weighted average of the atomic mass. So we're going to talk a lot about the mass. Why do you think there is a decimal on an atomic mass? Well, it's not the electrons. I used the example before that losing an electron would be the equivalent of losing a single hair. It's not going to change the scale, right? So what it actually has to do with is the different isotopes that an atom has, and they do a weighted average of the different isotopic masses in order to get the atomic mass that they put on the periodic table. Now, for our purposes right now, let's focus on a whole number. The idea is that the atomic mass would represent the number of both protons and neutrons. Let's think about that. Where is the mass of the atom found? In the nucleus. What's in the nucleus? Protons and neutrons. So you can't have a 0.01 of a proton or 0.01 of a neutron. So we know that for a single atom, regardless of which type of isotope it is, but for a single atom, we should have a whole number for the actual mass of an atom. So we're going to round this out to a whole number, and we're going to use the atomic number to determine the number of protons, and from that we should be able to determine the number of neutrons. If the idea is that both protons and neutrons contribute to the atomic mass equally, and nothing else does that's worth anything, then you should be able to do the atomic mass of 12 minus the atomic number of 6 to get the number of neutrons, also 6. The atomic number is the number of protons. I have 6 protons, and if I do the mass minus the atomic number, I should get the number of neutrons. Off the periodic table, you just wouldn't automatically assume we have an ion, so I wouldn't be changing the number of electrons. So I would also assume that it's neutral, and so I would also say there are probably 6 electrons. So this is something we're going to start doing, counting the number of protons, neutrons, and electrons. Let's practice some more. The first thing I want to do is introduce you to a new notation. In this notation, the chemical symbol would go kind of in the middle, and each corner would represent something different. The top left corner is the mass number, which will always be larger than the atomic number. So the numbers on the left are always top heavy. Top heavy. Mass number on top, atomic number on the bottom. On the top right would be where you would put something called a charge. So we have these things called ions, which could have a positive or negative charge, and that charge would go on the top right. The bottom right is left for something called a subscript. You may have seen like H2O has the little lower 2, so that would indicate that there's 2 hydrogen atoms. So we only use that usually with compounds, molecules, so that we can show how many of each atom there is. You're not going to see that when you're looking at an individual atom. Every single corner has a meaning. Now let's look at this carbon and see how many protons, neutrons, and electrons would be represented. The number of protons is always equal to the atomic number. So here I see on the bottom left the atomic number of 6, so that must be the number of protons. If there is no charge, then that would also be the number of electrons. The number of neutrons would be the mass number minus the atomic number. So for this carbon, it would be 14 minus 6, which would be 8. So for this carbon, we have 6 protons, 6 electrons, and 8 neutrons. I do want to mention, by the way, this carbon is a little bit different. Normal carbon would only have a mass number of 12. That's what we looked at on the periodic table earlier. This has a different mass number, which would make it something called an isotope. Now let's look at the nitrogen. For the protons, how many protons do you think there are based on this setup? Yes, the protons would be the atomic number, which is on the bottom left, 7. The electrons are going to be a little bit different because this time we do have a charge. We have a charge of -3. If I had no charge with 7 protons, then I would also have 7 electrons, which is what I've drawn here in this blue box. 7 protons or 7 plus signs and 7 electrons or 7 negative signs. That would have no negative charge. Now there are 2 options that I could use to get to a -3 charge. One option would be to take away 3 plus signs, which would leave me with only 4 protons. The problem is, any atom with 4 protons would be called beryllium and not nitrogen. So that does not work. So let's reset. The only other option to give me an extra 3 negative signs would be to add 3 more negative signs, which would give me a total of 10 electrons. When you have a negative charge, you have extra electrons. On the flip side, A positive charge could only be achieved by removing electrons. You cannot change the number of protons without changing the identity of the element. Now let's finish this one up with the number of neutrons. So in my nucleus I had neutrons and protons. The mass number up top gave me the number of both. So that would be our 15. But I know that 7 of those are protons. So I want to do 15 minus 7 to get the neutrons alone, which would be 8. So this nitrogen has 7 protons, 10 electrons, and 8 neutrons. I know I've mentioned ions and isotopes a few times, so let's define them, starting with isotopes here. Isotopes are a version of an atom that would have the same number of protons. That's kind of mandatory, right? But it would have a different number of neutrons. If it has a different number of neutrons, that means it would have a different mass number. Has to have the same atomic number, but it would have a different mass number because it has a different number of neutrons. And there's a special notation used a lot, especially with nuclear chemistry. What you do is you write the chemical symbol or the chemical name, and then afterwards you put the mass number. The reason you don't have to include the atomic number in this is because you could always just look that up on the periodic table. So let's try a couple of examples. Here I have my carbon 12 first. The 12, the given number, the only number that they give you, would always be the mass number. The atomic number would need to come from the periodic table. So let's look at your periodic table. What is the atomic number for carbon? 6. If I look at carbon 14, the only number it gives me for 14 would always be the mass number. The number given is the mass number. So then again, what's the atomic number for carbon? Well, it doesn't change. It's also 6. So let's count protons, neutrons, and electrons. Starting with the carbon 12. How many protons would there be? The number of protons is always equal to the atomic number. So that would be 6 protons. How many neutrons would there be? The neutrons is the mass number of 12 minus the atomic number of 6. So there would be 6 neutrons. How many electrons would there be? Keep in mind there wasn't a charge. You're not going to have an ion and an isotope simultaneously. So what is the number of electrons that would keep this neutral? Well, it would have to have the same as the number of protons, so that would also be 6. 6 electrons. Now let's look at the carbon 14 and count the number of protons, neutrons, and electrons. How many protons would carbon 14 have? Every single version of carbon will have 6 protons. That's what makes it carbon. What's the number of neutrons? Neutrons come from the mass number of 14 minus the atomic number of 6. So this one's going to have 8 neutrons. Now how many electrons? Yep, we still want to keep it even to the number of protons, so again, 6 electrons. The only thing that's different when you have an isotope is the number of neutrons, which means you have a different mass number. Now let's look at ions. Ions will have a charge. The only way to get a charge is to add or remove electrons. Remember, you can't add or remove protons without changing the identity of the substance. So this is going to come from adding or removing electrons. Now there are 2 main types of ions. Cations have a positive charge and anions have a negative charge. I have a kind of silly memory trick if it helps. So if you think of positive as in paws, like cat's paws, cats are positive. And then you may know that the prefix "an" actually usually has to do with not, which is kind of like being negative. So maybe that helps, but you have to know cations are positive and anions are negative. So that means they're going to have a little plus sign or negative sign up in the top right corner. The last thing we're going to do in Notes A is determine how to write something called a Lewis dot diagram or an electron dot diagram. The the number of dots is equal to the number of valence electrons. So the first thing that we have to do is figure out how many valence electrons an atom would have based on what column it is in the periodic table. In this column numbering, we do leave out the transition metals. As it turns out, they can actually have different numbers of valence electrons. So we're going to focus on everything but the metals in the middle. The first column will have 1 valence electron. The second column would have 2 valence electrons. Now if you skip completely past the transition metals, you end up on column 13. That's the third column we're numbering. So 13(3) kind of makes sense. That would have 3 valence electrons. Column 14 would have 4, 15 would have 5, 16, 6, 17, 7, and 18, 8. So from left to right, it numbers 1 through 8 if you just skip the transition metals. There is one exception, and that would be helium. We'll talk later about why helium belongs lined up with the other metals non-metals, with the other inert gases, the noble gases in that group 8. It does belong there for several reasons, but it only has 2 electrons. So it could only have 2 valence electrons. It wouldn't make much sense for it to have 8 valence electrons if it only had 2 total, right? So you should just know that helium is an exception, only having 2, but for the rest of the atoms on the periodic table, 1 through 8 from left to right. So with this in mind, let's try a couple. How many valence electrons does beryllium have? How many valence electrons does nitrogen have? How many valence electrons does krypton have? Good job, guys. Now that we know how many valence electrons need to be placed, we need to go over the order of placement. When you write a Lewis dot structure or an electron dot diagram, you put the element in the middle. So let's just use X to represent the element. Think of the element as being in a box, but you'll see in a minute we're not going to actually draw this box. I just want to make a point that there's a left, a right, a top, and a bottom. The first 2 dots will go on the right hand side. So that would be the first 2, dot 1 and dot 2. Then if there's a third dot, it goes to the top. Dot number 3 would go on top. The next dot would go to the left for the 4th dot. The 5th dot would go on the bottom. Then you would circle back. Notice how there's already 2 on the right? So my 6th dot would go back to the top. My 7th dot would go to the left. My bottom dot would go on the bottom. It really doesn't matter the placement of top or bottom, like how far up or down you're going when you're on one side. All that matters is that you do the first 2 dots on the right, and then you go top, left, bottom, top, left, bottom. It's kind of hard to describe why without having already learned more about quantum mechanics. Remember how we said there's only 1 s and 3 of the p's? Turns out those are the bonding orbitals. So we're filling the s up over here first, then we're filling half the p, half the p, half the p, and then we go back and we fill the other part of the p's. So that's kind of representing the type of bonding that the atom is doing. We have to be able to represent that per atom. So for right now, this is something that you just need to know the order of where to put the dots and how many dots. So let's try that with oxygen. If I'm going to draw an electron dot diagram for oxygen, I'm going to start by putting the atomic symbol in the middle. So for oxygen, that would be O. Now I want to look at my periodic table and determine how many valence electrons oxygen has. That's going to let me know how many dots to place. So how many valence electrons does oxygen have? It's in group 16, which means 6 valence electrons. So I'm going to place 6 dots. Where will the first 2 dots go? Both of them will go on the right-hand side. Where would the next dot go? On top. Where would the next dot go? To the left. Where would the next dot go? On the bottom. Where would the next dot go? On the top. Where would the next dot go? Oh, did I trick you? There's only supposed to be 6 valence electrons, so once we've placed 6 dots, we stop. This is the correct electron dot structure for oxygen. You wouldn't place a 7th dot unless you had 7 valence electrons. So if we were doing this for fluorine, yeah, we'd go to the left for our 7th dot. But we're only doing this for oxygen, which only has 6 valence electrons. So we're going to stop here. It does not matter how far up or down or left or right those single dots are, as long as they're on the correct side of the oxygen atom. That completes our first set of notes in Unit 2, Atomic Theory. The next notes you're looking for will be Notes B about light.